All right. Geometry lesson 49, introduction to solids. The figures that have been discussed up till now have all been two-dimensional figures. It's really hard to manipulate, work with a two-dimensional figure, but they're really easy to draw pictures of. Now, three-dimensional solids are easier to kind of handle and manipulate, as some of you guys are getting them handed around to you. You can hold them, look at them, mess with them, manipulate them, do what you want, but they're a little bit harder to draw. So this lesson introduces three-dimensional figures, what we call solids. Okay, solids can have flat, they can have curved surfaces, right? Some of you might have some of those, right? Right, I think, Jordan, you've got a sphere, you've got a cone. Right, anybody else have anything with a curved surface? Let's see, Marcos, do you know what that is called? It's got a cylinder, okay, so it's curved surface, okay? That does not have any curved surfaces. That is what we call a hexagonal prism, okay? So the surfaces of some solids are polygons, okay? Meaning that all of the sides that make up that figure are two-dimensional, closed, straight-line figures, right? What Chandler's got a triangular prism, okay? If we lay it on its side, it looks like a tent or a doghouse, right? But it's actually represented up and down like this with a triangle at top and bottom, okay? Let's see, what does Jose has? Jose has a whole lineup of pyramids, okay? I think there's, I don't know, did we dig any of those out? No. Okay. A hexagon. Okay, hexagon. All right, so any closed three-dimensional figure formed by four or more polygons that intersect only at their edges is called a polyhedron. All right, notice that it says four or more sides, and I think Jordan has one here. This is, you could call this a triangular pyramid, but this is actually a polyhedron that has the fewest number of sides that we can work with, right? Just the same way a triangle has the fewest number of sides that we can work with in terms of a polygon, all right? A triangular prism has the fewest number of sides that we can work with in terms of a solid. So everything else goes up from here in terms of number of sides, okay? Some other solids have circular bases or curved sides, like your cones or your cylinders. Okay, a cone is a three-dimensional figure with a circular base and a curved lateral surface. That's what Jordan has. Okay, has a circular base. Okay, and a curved lateral surface. Okay, unlike a pyramid. Okay, it's curved around. Okay, and it comes to a point. A cylinder is a three-dimensional figure with two parallel circular bases, not unlike Michael's hexagonal prism, but a cylinder, like what Marcos has, okay, has a curved lateral face, okay, that connects those two bases. So it operates like a prism in the sense that it has two bases that are parallel to each other, but how they're connected is by a curved lateral face. So a sphere is a set of points in space that are all a fixed distance from a given point. Does anybody, let's see, Jordan's got the sphere. Okay, I think we've got a couple of spheres in here. Okay, let's see, something like this. So what makes this a sphere is the fact that the outside edge, every point on the outside edge is the same distance from the center of that sphere as every other point on the sphere. Okay, same way with a circle. What makes a circle is that every point on the circle is the same distance from the center of the circle as every other point. Okay? All right. So we have down here, the best I could do to draw some pictures of some of these things with, ovals and lines and such. So we have a polyhedron, a cone, a cylinder, and a sphere. All things that you guys are holding and working with right now. Okay? But each of these things has different parts to it that we need to be able to identify, because you're going to get word problems in different scenarios where they're going to ask about this or that. Okay, and you need to know what it's talking about. So each flat surface of a polyhedron is called a face of a polyhedron. For instance, Michael's hexagonal prism, right? Anything that's not the base here, each of these sides is considered or called a face. Okay? So each polygon there that's on the sides that connects the bases is called a face. Okay? Same way with Katie's triangular prism. She's also got a hexagonal prism. Chandler's got a triangular prism. Even Jose's pyramids. It only has one base. It comes to a point, but each of these four sides is a face. Does that make sense? Okay? All right. So a vertex is where three or more edges come together. An edge is, I think we can identify a lot of these things. Edges are where two sides meet. Okay? And a vertex is where three edges meet. Okay? Let's see. So I think you guys kind of understand the visual, what all is being represented there, right? And then, of course, that vertex is where it comes to a point. All right, let's look at some other things. All right, there we've got our hexagonal prism is just a nice way. There we have our lateral faces and we have our two bases. So a pyramid's going to have one base, a cone's going to have one base. A prism is going to have two bases. Okay. Cylinder's going to have two bases. Okay, I don't know, what did I say? A cone's got one base. A sphere has no base. Okay, no base. Okay, so the base will either be at the bottom or the top and bottom. Now, one of the things that really messes people up is with a prism, say like a triangular prism like this, is that we can see the bases whenever we have a base at the bottom and a base at the top. But if I lay this down and say, where's the base, people will always point to the bottom. Okay, if I lay it on its side, the base is always the base. It doesn't change based upon how it's been oriented. Here's the thing, how we identify the base of a prism, is that it's always going to be the two sides that are parallel to each other. Jordan, if we can't not play with them, then I'm going to put them all back, okay? All right, I got to have you paying attention. Okay, I appreciate that you've got them, that you're interested in this, but I need you to pay attention. Yes, those two. Those two are the bases. Right, so those are your yes, but these are your lateral faces. These are only parallel to each other because you have an even number of them. Okay, so your bases will always be connected by your lateral faces. Okay. So orientation doesn't matter, shouldn't matter, okay? The same way, and it's a little bit easier to see it with like a cylinder. You know, if I said, where's the base? Well, obviously it can't be the edge that's on the bottom if I lay it on its side. Okay, imagine a can of soup, right? Just because I've knocked the can of soup over doesn't mean that the base has changed location, right? The base is still the parallel bases, okay? They're parallel sides of that. Does that make sense? Okay, so it's the same way with a prism. Those are just things that I see happen. But let's say we took a pyramid, right, and we put that on its side. Did the base move? Right? Did the base change? Did it move to a different side? No. Okay, so orientation doesn't matter. And they're going to show you pictures where the orientation has changed and ask you, you're still going to have to find the area, and because of that, you're going to have to know where the base is. A sphere does not have a base. A circle does not have a base. You're right. Now, a circle can be a base. Yes, okay, so like with the cylinder, the base of a cylinder is a circle. Okay? And the base of a cone is a circle. Okay? All right, so a pyramid is a polyhedron formed by a polygonal base. The fewest number of sides that it can have is a triangle, and I think we have some triangular pyramids, right, where the base is a triangle. Okay, It can go up from there. Here it could be a rectangle, it could be a square, it could be a hexagon. I don't know that we have any hexagonal pyramids here with us, okay? But the faces of a pyramid all share that common vertex. So that's where it's easy to determine which side is, even with a triangular pyramid, right? A little bit harder with a triangular pyramid, but you should see that they're all coming to the same point, and that point should be perpendicular above the base. Maddie, you're going to either have to get up or stand up, okay? So you got to stay awake, okay? So the base is the sides of the pyramid that does not share a single vertex with all of the other sides. Like I said, a little bit harder to see with a triangular pyramid than it is with a square, rectangular, or hexagonal pyramid, okay? The vertex should be easy to identify. It's that point where they all come to meet. Edges should be able to easily be identified. Yeah, stop stacking them. Okay, prisms. Okay, prisms and pyramids are named by the shape of their bases. Okay, that's why I called that a hexagonal pyramid, because the base was a hexagon. Okay, the base of a pyramid is going to be the name of the pyramid. So it could be a square pyramid because the base is a square, or a hexagonal pyramid because the base is a hexagon. Okay? You could have a pentagonal pyramid or a pentagonal prism. Okay? Now the difference between the prism and the pyramid is that in a pyramid, all of those edges from that base go to a single point. In a prism, there is an equal base at the other end that runs parallel to my base. Okay? Yep, you're going to do surface area, you're going to do lateral area, you're going to do volume. All right. Okay. You can keep that one. Okay. All right. So, and then in a cube, and I think I've got some cubes here. A cube is a special name given to a prism where all the lateral faces are 6 squares. Okay. So let's see. I don't know if this one I have one that's closed. I guess I do. All right. So all of the faces are the same size, have the same area. Okay. So it's made up of 6 squares. Okay, is a cube. I feel like I'm working mainly with things that you guys are familiar with, but we're just going through the names. No, this lesson is not surface area, lateral area, or volume, but we are going to get there. Now it'll be broken up over several lessons, so we'll do stuff with cones, we'll do stuff with spheres specifically, we'll do stuff with cylinders specifically, but it's going to be a lot of formulas. Now, I'll try to break them down in such a way that they make sense to you, that you understand basically that they have common principles involved. And so if you can remember those principles, it's easier to remember those formulas. But it's still, it's still stuff that you have to remember. A polyhedron is regular if all of its faces are congruent. So we could have a regular hexagonal prism, something like that. A pyramid is regular if its base is a regular polygon. So we could have a rectangular pyramid, or we could have a square pyramid. A square pyramid would be a regular pyramid. And I think mainly the ones that we have here are square pyramids, so these would all be considered regular. Okay? And then all of those triangles that come up, those lateral faces, are going to be isosceles triangles, meaning that they're going to have 2 sides that are congruent. Usually, it should be the sides that go up to that point. Okay? A prism is regular if its base is regular and its faces are rectangles. Come back over here to Michael's hexagonal prism. Okay? If these 2 hexagons are regular hexagons and these lateral faces are rectangles, meet those requirements. Let's see. A cube is both a regular polyhedron and a regular rectangular prism. A triangular prism is equilateral with equilateral bases. Okay, meaning all sides are the same length. Let's see. We're talking about a triangular prism. So like this one right here. If these triangles are equilateral, and for that matter equiangular, okay, then these three faces are going to be, should be rectangles, okay, is a regular prism, but is not a regular polyhedron since its faces are not congruent to its bases. Okay? That's what makes a cube a regular polyhedron. All right, this is where we get into the formula portion of this lesson. Okay, a diagonal of a polyhedron is a segment whose endpoints are the vertices of two different faces of a polyhedron. So not quite to the formula yet, but like let's say for this cube, I wanted to make a line that went from this upper corner down across to this lower corner. That would be a diagonal. Okay? It actually is going to create a hypotenuse. It creates a right triangle inside of it. And we'll solve some questions both in this class and in Algebra 3 that involve finding the length of that diagonal line. Okay? But it involves doing the Pythagorean theorem twice. Okay? We also see that there's a unique relationship that exists between the number of faces, the vertices, and the edges of any polyhedron, and this is what we're going to work with mostly today, which is how to find in a more complex solid, how can we find out how many edges it has if we know how many vertices it has and how many faces it has? Well, vertices minus edges plus faces will always equal 2. Okay, so I can always use that information. If I know how many vertices it has and how many edges it has, I can find the number of faces, or vice versa around. If I have two pieces of information, I can always find that missing piece. All right, Maddie, why don't you go ahead and stand up, kid? All right. So let's take a look at this. We want to classify the three-dimensional solid shown below. Is this a sphere? No. Okay. Is that a cylinder? No. Is it a rectangular prism? No. How do I identify the difference between a prism and a pyramid? Obviously, there's some differences of opinion on what this is. Okay, so a shape on the bottom. All right, so here I have a triangular prism. Over here, I have a triangular pyramid. What's the difference between these two things? Prism, pyramid. What's the difference? All right, so on a pyramid, the lateral faces are triangles. On a prism, the lateral faces are rectangles. Okay, how many bases does this have, this pyramid? The pyramid has one base, and 4 lateral faces. How many bases does the prism have? 2. How many bases will all prisms have? 2. How many bases will all pyramids have? 1. All right, so what is this shape up here? A pyramid. Okay. All right. Now, did we write down Euler's formula from the last page? Yes or no? Somebody did. Katie did. All right. It says use Euler's formula to determine how many faces a polyhedron with 20 edges and 13 vertices is going to have. Well, what was the formula again? Can you tell me? V minus E plus F equals 2. All right. So this has 20 edges and 13 vertices. We want to know how many faces it's going to have. So what do I put in for V? 13. 13 minus what? 20 plus F equals 2. All right, what's 13 minus 20? Okay, negative 7. Okay, so I've got negative 7 plus f equals 2. What do I do now? Add 7 to both sides. So how many faces is this going to have? It's going to have 9 faces. Okay? Easy enough to do, right? So long as you remember the formula, it's just add and subtract. Okay, so not hard, but you do have to know the formula v minus e plus f equals 2. All right, let's see. How many faces does this triangular pyramid have? And if it helps, if you have a triangular pyramid, Kobe, how many faces does that triangular pyramid have? It has 4 faces. Okay, and we see that there's one there, one here, and then one on the back side, right? It's kind of hard to see. This is why I'm telling you, three-dimensional solids are nice to work with when you have them in your hands. They're a little bit harder to work with when you're drawing pictures of them, okay? All right, edges. Maddie, how many edges does this triangular pyramid have? Six. 1, 2, 3, 4, 5, 6, right? Okay, 6. Chandler, how many vertices? What's that?
Counted as 8 edges.
As 8 edges?
Yeah, you know how they come up to the tip.
Okay. Here. All right.
Like, instead of the edge going like that one up was.
It ends at the, yeah, each edge ends at a vertex.
So wouldn't it be 8 then?
No, still just 6.
You got your
Look, 1, 2, 3, right? 4, 5,
Yeah.
6. Where am I getting 2 more from?
I'm just looking.
Okay, here. All right, try to, you're seeing 8. Let me erase and see. We do understand that this line comes all the way across, right? Yeah, it's cutting through all the way across the back side from that point to this point. Okay, so you're trying to make it maybe a, no, that's the same line. It's going all the way across. I see your point now. Okay. All right, Chandler, how many vertices does this have? 4. Okay. 1, 2, 3, 4. And you were seeing one like right here, I think. No, that's not. This is a line coming all the way up the front. All right, does we understand pretty much the basic concepts here? Okay. Can you guys collect those solids, try to put them back in that box for me?